All right. Well, good morning, everybody. It's great to see people here, and I think we probably have a number of people online as well. I have the pleasure, and it's a true pleasure, of introducing Mr. Ray Leonard. He is president of Anglo-Eurasia LLC, a consulting firm to the energy industry and governments on climate change and the energy transition. And he's also the chief operating officer of Linden Energy Holdings, which is a private equity funded firm participating in major gas and carbon capture and sequestration projects in Europe, Africa, and North America. Mr. Leonard received a BS honors from the University of Arizona and MA from the University of Texas, Austin in geology, hook 'em horns. He has held executive positions with Amoco, UCOS, and was most recently chief executive officer of Hyperdynamics, a New York Stock Exchange listed independent oil company exploring for oil and gas in West Africa. He has been active in publishing and presenting on world oil and gas reserves and climate change for many years at forums such as Council on Foreign Relations, International Energy Agency, the 26th World Gas Conference, and the World Economic Forum at Davos. So with that, Ray, welcome. We're looking forward to your talk.
Okay, thank you very much. Can everybody hear me okay? It's I'm not sure if this microphone is working, but it's not that large a room, so hopefully there's no problem. Well, thank you again, Mark, for inviting me to come and speak. It's always a pleasure to come back to the Bureau where I worked while I was a graduate student here. The subject of climate change is possibly one of the most controversial on this planet, and it's the problem is, first of all, that it encompasses virtually all the different sciences, from astronomy, biology, chemistry, through geology, oceanography. And very often people try to simplify it and say, well, this is the key to it. And in reality, it's an intensely complicated subject. The other problem is very often the presentations on it are advocacy presentations. Somebody has a point of view, and there's so much information that you can take the pieces of information that fit your advocacy point of view and base the presentation on that. What I've tried to do here is, this is not an advocate.
We've lost sound.
Just a second, Ray.
Okay. Okay.
Yeah, we're good.
Okay, I'm pushing this and it's not working to move it forward. Okay, this presentation basically has two parts. The first part is talking about the state of climate change, and the second part is regarding why the energy transition is so complex and it's not working as well as a number of people are hoping it will. The first point is, and I like to go over, tell them what you're going to tell them, and then tell them what you've told them. So this is a very quick summary of what I'm going to tell you. First of all, climate change the process is accelerating. In 2013, the IPCC put out a very extensive report, and they predicted a radioactive forcing factor, which is the change in the atmosphere, for 2030. And 2021, we've already surpassed where they thought we would be in 2013 in 2030. So things are moving faster than they thought. And this is due to what they call cascading impacts and compound events. In other words, they were reasonably good at predicting if this happens, this is the result. But what they weren't good at predicting is how these different factors interacted with each other. And in their 2021 and 2022 reports, they have tried to fix that. And in their report, and this is the entire 7,000-page report, not the 40-page executive summary, which is unfortunately a political document, they clearly state that the global temperatures will reach 1.5 degrees over pre-industrial time by 2030 and 2 degrees by 2050. That is baked in, and there's nothing we can do about that. And in this presentation, you'll see the reasons for that. The second half, in terms of the energy transition, is that despite the efforts that have been made in the past decade, fossil fuel use has only dropped from 88 to 85%. And so if you look at that sort of trend, the idea of going to net zero by 2050, I mean, you've got to do something dramatically different than we're doing now. One of the biggest problems is that the main sources of low carbon energy, hydro and nuclear, are likely not going to increase in the coming decades. And again, I will go over the reasons for that. And another problem is that the largest amount of resources are being spent in regions that have a declining share of the emissions, and also in many cases inefficiently. And another factor is we've had dramatic cost reduction in wind and solar in the past decade, and people are using that and trying to continue to increase that trend. And for reasons that are based on recent events, that's unlikely to continue. So let's get into the first half, which is the climate change. We have a number of tools that can identify temperature variations in the past that are beyond just the basic observations. And temperature variations are generally about a half a degree centigrade in years. You have extraordinary events that go past that, but generally it's about half a degree. And that's been fairly constant. And then about 500 or 600 years ago, temperatures started dropping in a period that was known as the Little Ice Age, which was due to reduction in solar radiation. And in the last 150 years, though, we've seen an extraordinary increase in temperatures. About a half a degree rise in the first half of the 20th century, and then a 1 degree rise just in the last 40 years, which is clearly outside the normal range. Something's happening here. And if you look in a little more detail at the last 150 years, you see that you hit a low in the first decades of the 20th century, and then you had a temperature rise of about half a degree over a 40-year period. And then from about 1950 to 1980, it was flat, even slightly decreasing. And then it's since 1980, the temperatures have taken off at a fairly steady rate of a 1/4 degree every decade. Now, of course, CO2 is pointed out rightly as a major factor in climate change, but here's a thought that we have to try to explain. The increase in CO2 was very minor until about 1950. It was only from about to about one gigaton per year. Then from 1950 to 1980, it increased by 500% during a time when temperatures were actually slightly dropping. And then it was only since 1980 that the dramatic increase in CO2 was consistent with the increase in temperature. So something else is going on here. So let's talk first about solar radiation. The sun has 2 seasons. It has calm and stormy. And in stormy, it actually gives out more radiation, which not surprisingly increases temperatures. This is a 22-year cycle from bottom to top. And depending on the strength of the cycle, it increases the temperature by about 0.1 to 0.2 degrees. Now, not all cycles are the same. And we've been able to measure these cycles from looking at sunspots, which we've been able to do since the invention of the telescope in the 1600s. There was a 50-year period when there were no sunspots. And not surprisingly, that was at the very bottom of the Little Ice Age, the lowest solar radiation. With time, the measurements have gotten better and better. And then since we've been able to put satellites into orbit, they have completely verified the science of sunspots and solar cycles. There's a larger cycle of about every 100 years in which the solar radiation cycles get stronger and weaker. And for the past several centuries, the first half of the century in general, the cycles get stronger and then they get weaker. And then at the beginning of the century, you have the lowest points. The Dolder minimum, which is the first 2 decades of the 18th century, were the 2 coldest decades since the Little Ice Age. If you take a look at from 1900 to 1950, it was a rapid rise, and the half-degree increase in temperature in the world in the first half of the 20th century was due to an increase in solar radiation. So there has been generally a fairly good correlation between solar radiation and temperatures. But if you take a look, but if you take a look at what happened after 1980, you've got a disconnect. After 1980, the solar radiation was dropping, but the temperature was rising. That's the period in which we've had this 1-degree increase in just 40 years. Now, physicists have put together models to try to predict the solar cycles, and this one is by Feynman, which has done a good job of predicting the cycles over the last several hundred years. And what he predicts, not surprisingly, is the most recent solar cycle was at the very bottom of the cycle, which is the same as you've had for every beginning of the century cycle for the last several hundred years. And what he predicts is that for the rest of the first half of the 21st century, the cycles will be going up again. That's bad news, because what's happened is that, bad as it has been for the increase of 1 degree centigrade over the last 40 years, the solar cycles have actually helped us. In other words, the rise would have been much greater if we hadn't been on the downside of this cycle. The bad news is, for the next 3 to 4 cycles, it's going to be the reverse, and it's going to be adding several tenths of a degree to the temperature. The bottom of this cycle was in 2020. We already have reached, in February of this year, the very peak of the previous cycle. So 25 is going to be stronger than 24. We don't know quite how much yet. I mean, the solar flares of this last month are an indication that this is going to be a strong solar cycle. So that's some bad news that we have coming up for the next 40 years. Another major factor is ocean currents, and the most powerful of the currents is the El Nino current. And as this shows, the El Nino is a warming of temperatures around the globe, whereas the reverse, a cooling current, the La Nina, is a cooling around the world. We've been measuring this for the last approximately 150 years. I mean, if you can put together an algorithm for these cycles, then you've probably done better than the smartest oceanographers in the world. But one point that is interesting is the 3 warmest, the largest El Nino cycles ever recorded have been since 1980, which is likely associated with the warming ocean. Now, when you go through temperatures and El Nino cycles, what you get is that for every degree of El Nino cycle, it increases the temperature by about 0.15 degrees. And for every cooling degree for La Nina, it drops it by 0.15 degrees. So this has an impact too. And of course, this is not so much affected with the atmosphere, but this is just under the normal variations. So what I've tried to do here is put a bunch of things together on one graph. And what it shows is that from 1950 to 1980, the overall temperature was about the same. And in general, you can see that the red is the El Nino. Those are the warm years. The blue is the La Nina. They're the cooler years. And then after 1980, you begin to have this background increase, which has to do with the atmosphere. The yellow suns are where you have the solar maximums. And what you see is in 1980, you've broken the world temperatures in the middle of a fairly strong solar maximum. This was the last strong solar maximum until it dropped. And then 2 years later, you match the world temperatures when you had an El Nino of greater than 2 degrees. Then at your next solar maximum, you broke the world temperature again. You had a several-month cool spell right after the Mount Pinatubo eruption, but that does give you an idea of this was the strongest eruption in the 20th century, and yet it only dropped the temperatures that much for that short a time. Then the 1998 El Nino, you broke the world temperature again. You matched it during the next solar maximum. Things stayed about the same. And then what happened is in the winter of 2015 and the early 2016, you had a collision of a solar maximum at the same time you had a strong El Nino. So what happened, you not only broke the world's record, you shattered it by several tenths of a degree. Since then, we have had something that just barely touched the level of an El Nino. It's been mostly La Niñas, except for a several-month period during the Corona lockdown. Now, I'll go over the reason for that in a minute. But what we're heading for here is the solar maximum is going to happen in 2024, 2025. We're at the bottom, it's going up, and it's going to be a stronger one than the last one. We're also heading into a strong El Nino. And maybe you've heard it here first, but in 2024, 2025, we're going to break this record. And we may even see what the world will be like at 1.5 degrees centigrade. You know, unfortunately, it is what it is. So that's the solar cycle, and that's the ocean currents. They have a significant impact on temperatures, and they're not as besides the atmosphere, but there's something we have to take into account. So let's talk about greenhouse gases. And the way that the IPCC uses the summary is with radiative forcing, which is the flux in the atmosphere due to natural or human-caused climate change in watts per meter. And the increase in since the beginning of the Industrial Revolution is about 2.8. And again, this surpasses the level predicted for 2030 from the 2013 report. So what I've done in this chart is I've taken all the different gases. It's interesting because this is not a chart in the report. This is something I've pulled out of the data from the report. And what it shows is that in the first half of the 20th century, the CO2 was rising just very slightly. But there are really three key gases here. There's the CO2, there's the methane, but there's also the aerosols, the pollutants. And the pollutants block the sun, and they actually reduce the temperature. So in the first half of the 20th century, you're putting out about as much pollutants as you were greenhouse gases. And so the temperature rise in the first half of the 20th century was due to solar radiation. After 1950, you had the world recovering. You had dramatic rises in CO2 emissions, but you also had what I call the golden age of pollution. Those were the years that we were putting an amazing amount of crap in the atmosphere. We may not have known what we were doing, but we were putting actually as much, if not more, aerosols in the atmosphere as we were greenhouse gases. And that's why the temperature was flat, if anything, dropping slightly. Interestingly, after 1980, the CO2 continued to rise, but as the US and Europe cleaned up their act, the amount of pollutants actually started to drop slightly. And that is why the temperatures started to rise after 1980. And you're now thinking to yourself, uh-oh, we got a problem, because if we do net zero, this stuff goes away. So what happens when this stuff goes away? We had, in the first half of 2020, a real-world laboratory experience of what happens in the world when that stuff goes away. Because in 2020, we should have had a very cool year. We were at the very bottom of the solar cycle. We actually had a La Nina, which was almost 1 degree. And we had the biggest drop in CO2 emissions that we've ever recorded since we've been recording this. So all these things should mean that things were cool. So what happened? In the first half of 2020, temperatures spiked, and they actually just about matched 2016, when you had a solar maximum and and one of the strongest El Niños ever recorded. But what happened? In the first half of 2020, we stopped polluting. This shows the pollution in China, January versus 20, January versus February. A picture is worth 1,000 words. This is the War Memorial in New Delhi in January, in January versus February. This is a calculation of the radiative forcing in the first few months of 2020. So in other words, you stop polluting and the temperature goes up. Now, if eventually, of course, it's good for you, because if you've stopped putting the stuff out, once you've taken the hit, you won't take a hit again. But the problem is, if you stop putting the aerosols in the air, according to the IPCC report, your temperature spikes by about 0.5 degree. So, I mean, that's your problem, and there's no way of getting around it. So let's talk a little bit about the greenhouse gases. First of all, with CO2, it's 80%. It's about 76% of your greenhouse gases, and 80% of it comes from fossil fuels. So it's mostly from fossil fuels. And as you know, as geoscientists, we can actually measure the CO2 levels in the geologic past from the fossil and the geochemical record. For example, during the Carboniferous glaciation, it was down in the 300 range, which is about where it has been recently. In the Permo-Triassic extinction event, it was at about 1,500 parts per million. And for those of you, for those people who said, well, gee, more CO2 is good for the plants, well, at that point in time, 90% of the species on the planet went extinct. It was at about 800 parts per million in the Paleocene, after the formation of at the time of the formation of the Antarctic ice cap. It dropped in half, and it dropped to the current historical level of ranging between 280 and 180 in the last million years during the glacial and interglacial periods. It rose from about 300 parts per million at the beginning of the 20th century. It's now at about 420 parts per million. It's going to hit 500 parts per million in 2050. And if we follow the most likely course, it's going to hit 600 by the end of this century. So we're entering territory that we have not seen since the Paleocene. Methane, a lot of people are assuming that methane goes up and down the same way carbon dioxide goes up and down, and that's not really the case. First of all, methane has increased since pre-industrial time almost twice as fast as CO2. CO2 has increased by about 150%. Methane has increased by 260%. Now, one big difference is that whereas CO2 increase is mostly due to fossil fuels, in methane, it's far different. About half of methane comes from natural sources like wetlands and melting of permafrost, and then half comes from human-based activities. The biggest single factor is agriculture. Fossil fuels, at the end of the day, are about 20% of methane emissions, of which 2/3 is from oil and gas, and 1/3 is from coal. And so when they talk about, well, we can cut methane 30% from oil and gas, and that'll turn things around. Well, that's good. We should do it. It will help. But if you take 30% out of 13%, you're taking 4% out of the total. So it's not the magnitude of the deal that people are making it out. Now, the other thing is that the methane increase has been dramatically increasing in the past decade, unlike what's happened with CO2. As a matter of fact, in 2020, we had the highest recorded methane increase since we've been recording methane increases at the same time that we had the biggest CO2 drop. So what's happening? Well, the problem is that due to climate change, certain things are happening, such as melting of the permafrost, and because of increased precipitation in certain parts of the world, increased emissions of methane. And you can say that by looking at a map and measuring the precipitation, but there's an even better way of measuring that. And that is because with methane, you have two isotopes of carbon, C12 and C13. And the ratio of C12 and C13 is different depending on whether it comes from fossil fuels and human-related activities versus natural-related activities. And what's happened since 2010 is that that ratio has sharply shifted. And what that is a clear indication that the methane explosion is happening due to factors outside of our control. And so, I mean, that's a problem. The methane has been decoupled from CO2. And your problem is that methane is a much more powerful greenhouse gas. Per molecule, it's 80 times more powerful in the short term and 25 times more powerful in the long term. That's because methane breaks down in the atmosphere. But the problem is when you take CH4 and you add O2 to it, it makes H2O, but it also makes CO2. So the IPCC report, which was the complete report in its 3 pieces, was 7,000 pages, but they put a lot of it into 5 different scenarios of future behavior. 2 that showed continued increasing of CO2 emissions, and 2 that showed significant decreasing, one of them reducing by 50% by 2050 and the other net zero. But what they also said was they put a qualification of how likely or unlikely they were. And the highest and the lowest they put as extremely unlikely to occur in their view, which is less than 5% chance. The second highest and the second lowest were unlikely, which meant about a 10% chance, which meant that the middle case, which is that we managed to flatten emissions and then start to significantly drop them after 2050, is extremely likely. That's the case that they believe will happen. It may not be the case they want to happen, but that's the case they believe. That somehow didn't make its way into the executive summary. Now, they show the 5 cases in terms of temperature change, precipitation change, and sea ice change, and they all say that it's going to get warmer, it's going to get wetter, and the sea ice is going to go away. But what you notice is that for the next 20 years, no matter what we do in those 5 cases, the result is the same. And the problem is, of course, that if you take away all the aerosols and go to net zero, your temperature spikes. Through 2040, you have virtually identical results. So it comes back to, we're going to be at 1.5 by 2030 and 2 by 2050, no matter what we do. So if we're going to be there, no matter what we do, then what the world is going to look like in 2050 is really, really important. And they spend 250 pages describing in great detail what the world is going to be like in 2050. And even though the global increase is 2 degrees, the land increase is going to be about 2.6 degrees, but even that is not consistent. Some places are going to be a lot warmer, the most being the Arctic, which is going to be 4 degrees. The Amazon and the Mediterranean are going to be about 3.5 degrees. The continental US is going to be about 3 degrees. So there are some places that are going to be a lot warmer. a lot warmer than 2 degrees by 2050. Now, in precipitation, it's going to be wetter, and some places are going to be a lot wetter. The polar areas are going to be a lot wetter, but there are some places that are going to be drier. And when you combine being drier with higher temperatures, that means considerably less precipitation in certain areas. And what the slide on your lower right highlights is areas that are going to have, okay, great, that are going to have significant, I use the word drought, but it's more than drought. It's a change of climate that's not going to turn around in the next 2 or 3 years. You may have 1 year that's suddenly wet again, but you're going to have significantly less precipitation and moisture. And that's the Southwest US, Central America, and the Amazon region, the Mediterranean region, and Southern Africa, and to some extent China also. The other factor is, and you've heard a lot about this, the tipping points. In the 2013 present IPCC report, they talked about tipping points, but these were something that far off. They were something like the day after tomorrow Hollywood movie that might happen, but we can't take them too seriously. The 2021 report, on the other hand, said these are things that can significantly happen to us. And a number of the scientists that were part of the 2021-22 report then went out and they ran their model and they tried to predict the tipping points that would happen at what temperature level. And this was presented in a landmark paper in Science in late 2022. And I think it's worth mentioning because the tipping points are where we have irreversible change, and irreversible means for the next centuries or even millennia. The Arctic sea ice, for the summer sea ice, we've already passed the tipping point. It's going to be gone basically by 2040. The winter sea ice, it has to get a lot warmer. The Greenland ice sheet, we will pass that tipping point by the second half of this century, although there's so much ice, it's going to take centuries to be gone. The Labrador sea convection, which is one of the ways that kind of protects the Atlantic meridian, that's going to be gone by 2040. The Atlantic meridian overturn, which I'll talk in a little more detail later, that they estimate somewhere in the 2.2 to 2.4 degrees, which could happen by 2010. The boreal permafrost by 2010. The Amazon rainforest dieback, that's also possible. I said 2010, I meant 2100. That's possible that it will be gone by the end of the century. The West Antarctic ice sheet, which again, I'll mention in a little more detail in a minute. The first glacier collapse is possible by 2050, which has implications for sea level change. It's going to take longer in the East Antarctic subbasin for a number of reasons, probably not this century. Then there are regional tipping points, which will change things in regions, but not globally. You are going to have in certain areas of the high Arctic an abrupt thaw beginning in 2050. The Barents Sea winter ice is almost gone. It'll be gone by 2050. Mountain glaciers in the low latitudes, they'll be mostly gone by 2070. Interestingly, they all predict this, that the Sahel and West Africa will turn green in the second half of this century. The low latitude coral reefs, they're almost 70% gone by now. Unfortunately, they're going to be completely gone. And eventually, as the permafrost disappears, the northern forests will begin to advance. So, it's not all bad, but it is what it is. I'd like to mention briefly the Arctic amplification. As I mentioned earlier, Arctic temperatures will rise twice as fast as the globe. Amazingly, since 1985, 50% of the surface area in the late summer and 70% of the ice volume has been gone. And by 2040, the only thing that'll be left is this skim of ice along the northern coast of Greenland, the Canadian Arctic. The rest of it will be open sea. So, you know, how does this accelerate everything? Well, one obvious thing is that when you have water instead of ice, you're absorbing 90% of the heat instead of reflecting 90% of the heat. The other thing is that, and this is on the verge of happening in the next decade, the Beaufort Gyre, which is a current which circulates ice here and keeps a lot of the fresh water in the Arctic to melt and evaporate, will be gone. And once that happens, the path of water from the Pacific through to the North Atlantic will be clearer, and you'll have a lot more fresh water, cold fresh water coming down here, which affects the Atlantic meridian. As the temperature differential between the Arctic and the temperate gets weaker and weaker, you begin to have these bulges in the jet stream causing polar vortexes and heat domes, which we're already seeing. It used to be kind of a once in decade thing. Now, every summer, we're finding these heat domes. And then there's the melting of the permafrost. There's an enormous amount of CO2 and methane from relics of the past ice age that are sitting under the permafrost. And one way of measuring just what this does to the atmosphere, this is a measuring of the atmosphere in Barrow, Atlanta at the time that the permafrost melted in that area there. This is in parts per billion. And if you remember the scale before, what we're looking at is an increase in the methane content of maybe 10 or 20 billion parts per billion per year. This is 200 to 300 billion parts per billion increase as it melts in those areas, which of course moves into the atmosphere. And when you consider the fact that somewhere between 15 and 20% of the world's land surface is covered with permafrost, as that melts, you can imagine the amount of CO2 and methane that's being supplied. So let's talk about two of the catastrophic tipping points that have a realistic chance of happening in the second half of the century that will have catastrophic impacts. The Gulf Stream, of course, it's basically a heat and moisture transfer from the tropics, goes along the east coast of the US, and it's the key reason why Northwestern Europe has a moderate climate as compared to the comparative latitude in Canada. The Gulf Stream has been weakening. It's now 15% weaker than it was perhaps 60 or 70 years ago. And the reason for that is that as the ice on Greenland melts, you're having an increasing stream of cold water coming down into the North Atlantic, which is blocking it. One interesting subpoint here is that as it's blocking it, the water temperature off the northeastern US is increasing faster than anywhere else, which is why the climate is changing faster there than many other places. A number of factors are going to be happening with Arctic amplification, such as the elimination of the Labrador circulation here, and then the Beaufort Gyre. This is going to be accelerating, and the oceanographers say that if the Gulf Stream reaches a 35 to 40% decrease in strength, it will overturn. Now, what happens if it overturns? Well, actually, we know exactly what will happen if it overturns because it happened 13,000 years ago. It's called the Dryas event. And from the ice cores that we have from the Alps and in Greenland, we know that in a 30-year period, the temperature dropped by 5 degrees centigrade. So we've been anguishing about 1.5, 2 degrees. Well, in 30 years, the temperature dropped 5 degrees. So a detailed model has been made, again, by these same scientists that show that if this happened, the northern hemisphere is going to get a lot colder and the southern hemisphere is going to get a lot hotter. And in addition, the whole circulation of currents is going to change, such as, for example, the monsoons in Southeast Asia and India are going to be gone. So this is a huge difference. Europe will not only get much colder, but it'll get much drier. The climate in Northern Europe will be the way the climate is in the same latitude in central Siberia. I spent 15 years working in Russia. I was in charge of their exploration program. I've spent winters in Tyumen, Krasnoyarsk, and Novosibirsk, and you don't want to live in Europe during those winters. The other key factor that really has a good chance of happening, I say good, I mean highly possible chance, it's not good by any means, is that breaking off of portions of the West Antarctic ice sheet. Now, the way the ocean currents work, most of the deep ocean heat ends up in the Antarctic current around, circling around Antarctica. Now, when we see Antarctica, we see this circle, but really the one half of the circle, East Antarctica, is land, and West Antarctica, except for a few isolated islands, is just ice. And so what's been happening is that warm current has been undermining that ice. And a number of the glaciers there have been under increased tension and the possibility of breaking off. Again, what happens if large pieces of it break off? Well, it happened, and it's called meltwater pulse 1. It was 14,600 years ago. At the end of the last ice age, sea level rose by about 100 meters in 10,000 years, which is about 10 meters per year, but it wasn't a consistent move. It went in pulses, and the meltwater pulse was 18 meters of sea level rise in 500 years, or 1 meter every 28 years. Right now, sea level is rising at 4 millimeters per year. That would increase it by an order of magnitude if pieces begin to break off, which is likely going to happen. So, as I said before, we've had, since 2016, we've had a bit of a holiday because of the solar minimum, because of the La Niñas. Well, that's coming to an end. Last year, we had 5 of those heat domes at one time. In February, we already reached the peak of the last solar maximum, and La Niña ended at the beginning of this year. In a remarkably short time, we passed through neutral. We're now hitting El Nino, and the prediction is it'll be at 1.5 degrees positive by the fourth quarter of this year. So get ready for a really warm 2024 and 2025. So let's move to the second half of the presentation, which is how do we measure our progress in the energy transition? And you can do that in a very simple way by looking at 2 things: the amount of energy we use and the amount of CO2 emissions. And what I've done here is because you have large variations in individual years because of recessions and expansions, I've used a 10-year rolling average. And for the past 45 years or so, we've really had 3 periods. The first period, from 1982 to 1995, was a gradual decline in the amount of energy use and a fairly constant ratio of about 0.9 in terms of the amount of CO2 increase and energy increase. And that was because after the cost of oil increased by a factor of 10 in the late 70s and early 80s, people started getting more efficient in terms of using their energy. We started buying smaller cars. And that trend carried on through the 1990s. So part number 2 is what I call the rise of China. It's difficult to overstate just how big the rise of China affected energy use. The energy increase amount almost doubled to about 2.5% per year. And because most of the energy was powered by coal, the proportion of CO2 versus energy actually increased to a ratio of just above 1. And gradually that flattened out in the latter parts of the first decade of the 21st century. And then for the past decade, we've gone into what we call the energy transition, which actually has made some progress. We've gone into a period in which the energy use increase has averaged about 1.5% per year, and the ratio of CO2 emissions increase has been about 0.5% per year. I mean, the CO2 emissions are still going up, but they're only going up about half as fast as the energy use. If you try to put a trend in it, you say, okay, well, maybe we'll hit the emissions plateau in 2035, which is actually where the IPCC came out in terms of that possibility. The problem is that this doesn't solve our problem. All this does is flatten at a rate that's increasing our temperature by a quarter degree every decade. So what are the obstacles to try to move this faster? Problem number one is China. Just taking a look at how things have changed since 1950. In 1950, the US had half of the world's emissions, the EU had 22%, and China had 1%. In 2021, combined, the USA and EU were only 22%, and China was 32%. And if we continue on the current trends, by 2030, we'll be below 20%, the US and EU, and China will be at 40%. And the key factor is China burns more coal than the rest of the world combined, and they plan to increase their coal use by 300 million tons in the next 5 years. And what's happened in China, because they're struggling to try to hit their growth targets, leadership is going to increase their dependence on low-cost coal, and there's going to be less money for subsidies for renewables. So unfortunately, things are going in the wrong direction in China because they're focusing on economic growth. Now, China has had some green initiatives, but the problem is that those green initiatives are actually, in many cases, counterproductive. China produces and sells about 55% of the world's electric vehicles. Unfortunately, most of them are powered by coal. So when you calculate it, a China electric vehicle has a higher CO2 signature than internal combustion energy vehicles. The other thing China's done is shifted dramatically to hydropower as much as they could, so that 30% of the world's hydropower now is in China. The problem is that it depends on water, and China's got two problems, as I'll mention later. One is that it's going to be facing serious drought due to China's climate change, which it experienced this year. And the other is that a lot of the water is based on glaciers, which probably will be gone in the second half of the 20th century. The second problem we have is geopolitics. And these are things that have just happened in the past few years. Now, what China has done very efficiently is, over the past 20 years, put themselves in a position where they are in a commanding position in the global supply chain for processing of critical minerals. And what is happening over the last 2 or 3 years is a decoupling between China on one hand and the US and the EU in terms of trade relationship and in terms of working together on these factors. Now, the US is trying to reposition itself, but that's going to take time. And to dramatically increase our use of these critical minerals at the same time that we're trying to reposition the climate change is going to be a stretch. Your second problem is the Russian invasion of Ukraine. Now, removing Russian gas from Europe and restricting oil and oil products, particularly for gas, it's increased the prices so that a number of countries around the world, particularly in South Asia now, a dramatic shift to gas is not in the cards because they simply can't afford it. So what are they doing? They're going back to coal. And the predictions are that at least for the next 5 years, coal use is going to be, if not flat, it may even actually be increasing. Your other problem is that if you're going to try to shift to nuclear, Russia has 52% of the world's capacity for enriched uranium and supplies about 40%. So if you're going to try to dramatically increase uranium, you're going to have to work with Russia. And is Russia going to be workable? And the third problem, it's a more general one, is that the global order that was led by the US since the end of the Cold War is breaking down. And because it's breaking down, nations are focusing more on energy security, and trade barriers for the flow of natural resources and processed materials are rising. A third problem is climate change. And the impact of climate change will have a significant negative effect on at least two sources of low carbon energy. One is, as I've indicated before, is drought. You've got 5 areas in the world in which you're going to have significantly less precipitation, and those areas actually depend heavily on hydropower, and you're already seeing a problem. And 2022 illustrated that. It's the Southwest US, Brazil and Argentina. South America gets more than 50% of its electricity from hydropower, and because of the drought last year, they actually had to import LNG. The Mediterranean, which had 40% less power from hydropower last summer. Southern Africa, if you've ever seen pictures of Victoria Falls, well, now it's known as Victoria Trickle, because virtually no water is getting down the Zambezi River. And China. There's another problem in that a lot of these areas are also dependent on the glaciers for the water for hydropower. And there are 5 areas: the Pacific Northwest, the Central Europe Alps, the Caucasus, South Asia, and China, where these glaciers are going to be gone by the end of the century. Your other problem is with wind power, because wind is basically generated by temperature differentials. And your problem is, as the temperature differential between the polar areas and the temperate declines, it also reduces the amount of wind. And this is just a northern hemisphere phenomenon, but unfortunately, that's where most of the wind power is. And the models, again, by these same IPCC people, show that the amount of wind energy is going to be decreasing as the temperatures rise, 5 to 10%. And the higher the temperature rises, the bigger the decrease. And unfortunately, a 5% decrease in wind speed means a 15% decrease in wind energy. 10% means a 30%. So you're going to have a significant amount of decrease in your installed wind energy, in your capacity. It is what it is. Your next problem is misallocation of resources. In the past 50 years, the amount of CO2 emissions from the OEDC countries have dropped from 2/3 to just 1/3, and that'll drop below 25% in 2030. Now, the amount of money being put into clean energy is starting to increase. Your problem is, where are you putting that money? In 2014, the OEDC countries had almost 40% of emissions, and they were putting in about 50% of the money. And the emerging nations had about 1/3 of the emissions, and they were putting in about 24% of the money. Fast forward to 2021, and the advanced economies had only slightly more than 30% of the emissions, but they were putting in more than 50% of the money into their economies. The emerging nations had something on the order of 36% of the emissions, but now they were only putting in about 15% of the money. So the trend is going in the wrong direction. Despite all the talking and efforts, it's going in the wrong direction. This is why the UN Secretary General is pulling out his hair about this, because of what's happening. And just to emphasize the fact, in 2022, global emissions increased by 0.9%, but they increased by 4% in the developing economies. Obstacle number 5, the exponential growth of solar and wind that they've been counting on is not sustainable. 2011 to 2020 was highly favorable for the development of wind and solar. Everything helped it. There was technology advancement, there were low energy costs for construction, there were subsidies, and it actually became cost competitive with gas and was preferable to nuclear and coal. Now, the installed capacity grew by 570%, the consumption by 400%. And right there is a little bit of a warning sign, because when your consumption is going less than your capacity, it means that somehow you're starting to become less efficient. Now, the combined share of world primary energy increased from 2.6 to 6%. So it was significant, but if the world is going to run on wind and solar, you're going to have to go a whole lot better than 6%. So what's happened in the last 2 or 3 years? We have, for one thing, energy is a lot more expensive than it was, and constructing this is all energy intensive. The other problem you have is a shortage of critical minerals, because as we've ramped up the production of solar panels, wind turbines, and batteries, we've now hit a ceiling on the amount of critical minerals that can be produced. So we're going to have to ramp up the production. In many cases, it's not multiples, it's orders of magnitude. Unfortunately, it takes time to build up these facilities, 5 to 15 years. So the higher prices for the critical minerals, unfortunately, are here to stay. So I believe the renewable capacity will continue to rise, but it's more going to be like a geometric. It's not going to be an exponential rise. It just is not going to happen. Next problem is your inability to grow nuclear power. Now, nuclear power was started in the 1960s. It actually hit a peak in 1996 when 17.5% of the world's power came from nuclear. And this year we passed a milestone. We went below 10%. So again, we're going in the wrong direction. And nuclear is actually the safest way of generating electric power in terms of the amount of deaths per kilowatt generated. Since 1990, we have retired as many electric nuclear power plants as we have built new ones. And your problem is that if you take a look at the chart of when they were built, a huge amount were built in the 80s and 90s, and they're approaching the end of their life. So by 2040, almost 40% of all existing plants are going to be retired. So you're going to have to build a hell of a lot of plants just to keep nuclear at the level that it is now. That's probably not sustainable, especially since it takes almost 10 years now for the construction of new nuclear reactors. And adding on to the fact that Russia supplies almost half of your actual fuel supply. So don't look to nuclear for an answer. You'll be lucky to keep nuclear at the same level it is now. And finally, we look at solar power, and the efficiency of a solar panel ranges from about 10% to 35%. I mean, obviously it doesn't work at night, so that cuts you from 100 to 50. And then it has limited ability right at sunrise and sunset. So if you're sitting in the Sahara Desert or another place, 35% is about as good as you can do. And that map shows you the variation in terms of the amount of solar radiation. It depends on latitude, and actually I should say latitude, altitude, and climate. And the indicators I have there show different places of which people are building solar plants. And there's a huge difference in terms of the calculated efficiency for those places. And if you take a look in the best of all worlds, what you'd see is most of your solar energy being installed in the places where you have the greatest efficiency. That's what you think would happen, right? Well, that's not exactly what's happening. The two bars in the chart in the upper right, one of them shows the percent of the electric grid in these different places, and the other is capacity installed in 10 gigawatt intervals. And what it shows is that in a lot of the best places for installation of solar power because of the efficiency, like Egypt and South Africa and Pakistan and Brazil and India and Iran and Turkey, you have very little solar panels installed. They're just several percent at most. The only two places where they really have done a good job that have a high efficiency are the southwestern US and Australia. On the other end of the cycle, you've got Great Britain, Netherlands, Germany, South Coastal China, where your efficiencies are only in the 10 to 15% range, where you put enormous amounts of capacity in there. This is why the worldwide average efficiency for solar panels is only 15%. If you spent the money that you spent building solar panels in Germany, Netherlands, Great Britain, and France, and put it into Egypt, South Africa, Pakistan, and Brazil, you would triple the amount of actual energy you could get, and possibly reduce their use of fossil fuels. So finally, we come to implementation of new technologies. And 6 technologies were developed in the second half of the 20th century that have formed the basis for the alternatives for lower carbon energy. And it's why we've been able to cut in half the rate of greenhouse gas emissions. It's nuclear power, LNG, combined cycle gas turbines, solar voltaics, wind energy, rechargeable batteries, which is still ongoing as we get new catalysts. And on average, it has taken 40 years from when you had the aha idea in the laboratory to when you actually had full commercialization. It's varied a little bit, but that's a pretty consistent number. So there are 5 technologies we have now that can actually turn things around and reduce the amount of greenhouse emissions. There's small modular reactors, carbon capture sequestration, hydrogen, direct air capture, and nuclear fusion. And in some of these, you've got a wide gap because they were in use, but not commercial use. So modular reactors, for example, for military, carbon capture and sequestration. It was for EOR, which is a niche. It wasn't for full commercialization. And those will come into play over the next 30 or 40 years, but it's going to take time based on historical precedent. So in conclusion, hard truths. The world is going to reach 2 degrees above pre-industrial temperature by 2050, and we need to prepare for the consequences. And we're heading for 3 degrees by 2100, which increases the chances of catastrophic tipping points in the second half of the century. And what we need to recognize is that there are factors that are out of our control. One is solar radiation. We're unfortunately going into the cycles that are going up. The aerosol effect. If you cut out burning fossil fuels and cut off the aerosols, it's going to increase your temperature. Climate change. What's happening now is unfortunately hindering the energy transition. Methane increase. Methane has been decoupled from CO2. We can do things to reduce methane, but that's just a small fraction of the overall process. And finally, reality of what net zero means. What net zero means is we've frozen the atmosphere levels at what we have now. And what we have now is increasing temperatures by 0.25 degrees every decade. And if you think about that, you see how hard it is to keep us from getting to 3 degrees by the end of the century. If we get to net zero, all we're doing is freezing the increase rate that we have now. So what can we do? Accelerated utilization of existing technologies that we have proven to work in a more efficient manner. Introduce economic stimulus incentives to speed the rapid commercialization of the new technologies, and devote commensurate resources to regions in which emissions are currently increasing. So that's the world as I see it. And a summary statement can be that if you don't deal with reality, reality will deal with you. Thank you.
Thank you, Ray. That was truly a informative and broad talk, touching on just all the complexities that go along with this topic. So very much appreciate that. And open it up for any questions, and I'm sure there should be a few, at least.
I was told actually after I gave one presentation to one of my corporate customers, he said, Ray, never give that talk in a tall building with the window open.
Yeah, well, great presentation. Thank you. I would like to know if you were talking about the solar radiation and the Niño and Niña currents. So
Right.
could you explain a little bit more what's the relation between both of them? Because, you know, the current comes out of some reason, you know, how it's changed so dramatically should have some connection with the solar radiation. And that's what I was trying to see in the graph. What's the correlation between the solar radiation and the Niña and Niña? Okay. And the second question will be, and how much those two are contributing to the global warming beside, you know, the human causes of CO2 emissions and all that. And the third and last question will be, were you planning to advise your kids and your family to move? Where's the safe place to live in this world?
Okay, well, the first question, and actually I was going along the same path, which is why I constructed this graph. I tried to put all the things together. And the first point is that the solar radiation is based on solar physics. And we little people on Earth have nothing to do with that. It will happen when it happens. And the best we can do is to try to figure out why it happens and try to put together a predictive model. And the solar scientists go on it in two different ways. One of them is measuring what goes on in the sun and trying to understand the solar flares. And the other is from a statistical standpoint, looking at the ups and downs of the past 300 years and trying to put together patterns. And that's where you got the Feynman solar model. He's on the statistical side. You know, we'd have to go into detail in solar physics, but it's completely outside of our control. Now, with regard to the El Nino and La Nina, again, there doesn't seem to be a clear pattern, but there seems to be a strong body of oceanographers who believe that as you're warming the ocean, your El Nino cycles will get stronger and stronger. And they use as an example, the 3 strongest cycles that have ever been measured have been in the last 40 years. So from the standpoint of I'm not sure what we're doing affects when the La Niñas and the El Niños happen, but with a warming ocean, it could be that your El Niños will get stronger. And the one thing that has been established when you look at all the temperatures and you put them all in, is you get a pretty good correlation of, for every degree of El Nino, it increases the temperatures by 0.15 degrees. So that's the best I can do on answering that question. So your second question was, you know, again, if you take a look at these, they're separate things. They're completely separate things. But what you have to do is, when you look at them, you know that when the two happen at the same time, you're going to have an increase in temperature of almost 0.5 degree. And what I'm afraid of is that in 2024, 2025, the two are going to come together. And from what you saw in 2015, 2016, I think we're going to get a glimpse of what the temperatures are going to look like in the 2030s in 2024 or 2025. And it's not going to be pleasant. Maybe it'll get the world's attention enough to do something, but we'll see. The third piece is, I live in Houston, Texas. I'm not sure I want to live in Houston, Texas in 15 or 20 years from now. Now, at my age, it may not make any difference, but I think that that coastal places at low sea level are really potentially a risk. You're a lot better off being here in Austin, although there are other reasons you're better off in Austin too, but yeah.
Thanks. That was a very enjoyable, or maybe not enjoyable, the right word, convincing compilation and things you put together. I hadn't seen them all put together that way. It's very fun.
Thank you.
About 15 or 20 of us in the audience anywhere are working hard on CCS. We're with you. You know,
Mhm.
we bought the message, including the international aspect. You know, I was on this morning talking to people in the UK about, okay, how are we going to get people from Indonesia to our meeting? So we
Yeah.
also buy this part of the story. But I wonder about the tall building and the open windows and the desperation issue. You've assumed that these impacts are additive. And usually there's interference too. For example, albedo and cloud cover and the increasing moisture content, you know, is always in thunderstorms and how that dissipates energy in the atmosphere. I mean, there's probably some things that also trend the other way that bring it back. And I wonder if there's ways to find them and use them.
Well,
To things that, I mean, we talk about drastic things like in substituting aluminum foil particulates in the atmosphere or something. But I wonder if the hope we could find stuff that
well, the IPCC report actually has a section on potential mitigating matters. And again, it's interesting as geoscientists and climatologists, if you look at the past, nature has produced experiments, just like in 2020, when we stopped industrial activity, it showed us that the temperatures will spike by about 0.3 or 0.4 degrees. In 1815, you had a huge volcanic explosion called the Tambora explosion, which was the largest in the last 500 years. And you had a amount of volcanic ash that was put into the atmosphere that was at least an order of magnitude more than Pinatubo. And so the year after that was known as the year without a summer. The temperature dropped worldwide by about a degree. The problem was that it dropped worldwide by a degree. In some places, it dropped considerably more. In some places, it didn't drop at all, number one. And number two, it completely disrupted the climate from the standpoint of rainfall. And so one of the problems with that is the volume that you've got to put up there is incredible. I mean, the fact that Pinatubo only was able to have this effect is sobering. And the second problem is that, be careful what you wish for, because, for example, it could stop the monsoon in India. And the worry is that if you get sophisticated enough in your climate models, a country could say, well, okay, this is disastrous for them, but it's not so bad for us. I mean, one of the problems is that this whole climate change thing, on balance, for Russia, it's a balance. Whereas for India, it's an unmitigated disaster. For Russia, it's a balance. Their Arctic coast is now ice-free. The growing season in Siberia has doubled, So are people looking at mitigations? Yes. Has anybody come up with one that's a silver bullet yet? No. So.
Well, I think we shouldn't jump out of tall windows. I think we should
No.
work harder on mitigations.
No, well, it's just,
We want mitigations.
it's just a warning.
Let's see, one more question in the room, and then Michael, do we have any questions online at all? Okay, not a question. Okay, so we'll probably make this the last question unless there's another burning one.
Thank you. Thank you for the presentation. So I had like two quick questions to you. So you discussed, different kind of renewable energy. I was expecting that you might mention geothermal energy, because now a lot of research work is going on here, especially in the US, about geothermal. So I would like to know what is your point of view about geothermal energy development for solving the problem. The second point of view is, since I'm from Egypt, okay, so and you spoke about investing, the uneven distribution of investing, in minimizing. But my point of view, how you convince, emerging country or developing country to put more money, for a global warming, and they also suffer. They already had a problem in their economy, and they can come and say, "Hey, we did not pollute. We are not the cause of the problem." So, what I'm thinking about that is more fair that US and Europe give more incentive to this country, even give to China, right? Because you cannot go to China now and say, hey, you have to stop your development to save the environment.
Okay, well, the first point is that there's a whole range of different technologies. I mean, from geothermal to biofuels to helium, et cetera. And the question is, can you get it to scale where it's looking at, does it have the possibility of getting to at least several percent of the world's energy supply? And you know, I do agree that geothermal is a possibility. The question is, can you get it up to scale within this time distance? So I wouldn't say no to it. It is a possibility. And in regional areas where we have a high geothermal gradient and the other things, it could produce 10 to 20 to 30% energy in certain areas. I mean, look at Iceland. So it's right now it's a niche solution. I don't see it as a solution on the scale of solar and energy right now, or solar and wind. On the other question, what has to happen is the advanced nations have got to start being more effective in the way they're using money themselves. I mean, you've wasted huge amounts of money building solar panels in Germany and the Netherlands. If you had taken that money and built it in Egypt, you would get 3 times as much benefit. There has to be a fundamental change in the resource allocation. And it comes back to something I said earlier. I believe in 2024, 2025, we're going to break the 2016 record, possibly even shatter it. And it could be that what happens there has such an impact that people step back and say, we can't go on the way we're going now. Unfortunately, I believe it's going to take something like that to do it. But that's what has to happen, because Egypt does not, and it's not just Egypt. It's if you look at that chart of the countries that have excellent solar potential, yet have less than 2 or 3% of their electricity grid and solar energy, it's a scandal. And then you look at the number of countries with 10% efficiency that have 10% of their grid on solar. It's crazy. And so something has to happen to change that.
Well, Ray, I want to thank you again for the talk. I mean, it's very thought-provoking. And so let's have another round of applause.
Okay. It will be online for people to access. It's a public document, and you have my email on there. You're very welcome to send me comments or questions. Okay, thank you.